You should be seeing full screen now.
Now it is. Yep, looks great.
Okay, excellent. So I overcame technology once again. So this month we're going to do part 3. This is the last of 3 parts. And this is going to be the measurements that I've taken since about 2008 or 2009. At least one complete solar cycle and part of the one that's going right now, solar cycle 25. So before on part 1, we talked about geomagnetism kind of in general terms. And now we're going to look at specific data that I've taken. And there's actually some pretty interesting stuff that you'll see once you get your mag going. And the first thing I want to talk about is magnetogram. This is produced by the SAM magnetometer once you have your software set up. And magnetogram is generally a 24-hour time base. And so you can see on the horizontal scale here that it's broken up into 3-hour periods, and those are called synoptic periods because the K index, which is a really popular magnetic index, is based on activity within 3-hour periods. And they're standardized 0 to 300, 300 to 600, and so on. So that's the time scale that you're going to see, 24 hours long. And then on the vertical scale of the magnetogram that the SAM produces, you're going to have um, uh, values in nanotesla. So this is the magnetic flux density that's being measured by the 3 axes. And you can see there's 3 traces, and they're color coded. And then down in this magnetogram, you can see the key. So red is BX, which is north-south. The blue is Y, which is east-west. And then the green is BZ, which is vertical. And you can turn on and off any one of these curves. You can uh, just run or display one curve, or you can display all 3. It's up to you. It's completely customizable. Now, I mentioned, I think the last time, that the SAM3 operates as a variometer. And what that means is that it's plotting the change in magnetic field. And the change is with respect to midnight of that day, of the current day. So every midnight, just before midnight, the SAM3 software normalizes the data. And then when it starts the next day at midnight, it will display 0 for all 3 traces. So in other words, these values are not the actual magnetic field values. What's being displayed is the change in the magnetic field values over the time period displayed here. So, and you can change that. The software has a feature where you can turn that off basically. And so whatever offset is shown at midnight, it's going to continue on into the next day. So, but in the spring and fall, when your temperatures are changing fairly rapidly, the traces are going to go off scale eventually. So it's best to operate it as a variometer, as shown here. And there's been people that have tried to calibrate, and the SWUG group in New Hampshire, they have the professor there has some contracts with NASA, and he has all the calibration facilities for magnetometers. He works on the actual spacecraft. So he's done this, and the software setup guide has information on how to use the values that he came up with. But otherwise, this is an uncalibrated system. So it's a simple variometer. Now, as far as magnetic disturbances goes, there's the major sources are listed here. There's solar flares, which normally do not have a direct effect except for the one exception shown here called solar flare effect. It's a real imaginative name for it. But a more imaginative name is a magnetic crochet. And I'll show you one of those. They're very rare, and but I have captured, I think, 2 or 3 in the last 15 years. The coronal mass ejections, that's where an enormous mass of particles is ejected from the sun's corona. And if that CME intercepts Earth in its orbit around the sun, then there's a fairly good chance that there's going to be a magnetic disturbance associated with that. Now, it doesn't happen every time. It depends on the magnetic field in the CME, how it's oriented with respect to Earth. And I'll talk more about that a little bit later. The other source of magnetic disturbances are coronal hole high-speed streams. Now, what these are the enhanced solar wind, and these are probably the major source of disturbances. There's coronal hole high-speed streams going on almost all the time, and they interact with Earth's magnetic field and cause problems. Co-rotating interaction regions are shock fronts that are associated with the coronal hole. So this fast solar wind catches up with the slow solar wind, makes a shock front, and that'll intercept Earth, and that could cause problems depending on the orientation of the magnetic field that's embedded in there. And then the last one is solar sector boundary crossings. And this is basically wobbling of the heliospheric current sheet that connects between Earth and the sun. And I'll show you examples of magnetograms associated with each one of these. Now, for the most part, magnetograms are just squiggly lines on a graph. And many times you can't tell that the source was a coronal hole, a solar sector boundary crossing, or whatever. You don't know that. And you can't tell that on Earth. But there's spacecraft out there that are specifically designed to recognize things like that. So you can get reports from the the Space Weather Prediction Center that gives you that kind of information. So you can make a correlation between what they see on a spacecraft and then how it affects the magnetic field on the ground that you're actually measuring. So now all magnetic disturbances involve one way or the other the sun's magnetic field. The solar magnetic field is embedded in the solar wind plasma, and it's basically it's frozen in. So if there's any movement in the plasma, the magnetic field moves along with it. If something moves the magnetic field, the plasma is going to move with it. So they're fellow travelers, and that's one of the key things that you need to remember about the sun's magnetic field is that it's embedded in the solar wind, and then the solar wind impinges on Earth. Now, CMEs take about a day to a week or so. Really fast ones will get here in a day. Generally, it takes a couple days or so to get to Earth. So if you read about coronal mass ejection and the Space Weather Prediction Center says that it's Earth effective, then it could be a day or so or up to a week before you actually feel it. Coronal holes, a couple days or so. When you have a solar flare, you've got instantaneous effects from the radiation. And I'll show you that here in a little bit. Now, the solar flares, as soon as you have a flare, you have a huge range of wavelengths that are emitted by or radiated by the sun. And those are instantaneously felt on Earth. And when I say instantaneously, I mean that it's an eight and a third minutes before it actually occurs on the sun, before we see it on Earth. But that effect is only felt and displayed as so-called solar flare effect that I mentioned. Now, you also have solar energetic particles that are emitted by a flare. These take anywhere from a few minutes to several hours to reach Earth. And these generally, if there are energetic protons involved, it affects radio propagation much more than it affects Earth's magnetic field, except at higher latitudes where I'm at. I can see the effects of that, of energetic protons, and I'll show you that a little bit later. The CME itself, once it reaches Earth, then it's preceded by a shock wave, and that shock wave can cause what is called a sudden impulse, and so it's like hitting a balloon when it hits the magnetosphere, and you see a pulse on your magnetogram, and that is the only time you'll see a really rapid rise in the magnetic field. There's no such thing as a step increase, but it's fairly close to it. Might take tens of seconds rather than microseconds for a step increase. Now, one of the key things about disturbances is knowing about the Dungy cycle. This guy was really smart about how the solar wind works. And back in the early 60s, he came up with this idea that, and which is called the Dungy cycle after him. And what you have is if you have the solar wind magnetic field has a southward pointing component as shown by the red lines over here on the left. When that reaches Earth's magnetosphere, the Earth's magnetic field is south to north. So the solar magnetic field is opposite to Earth, and it is able to reconnect. Remember that unlike poles of a magnet attract each other. So there's what is called magnetic reconnection. Was there a question? Oh, it was a dog barking.
Paul, I'd suggest you go through all the participants and mute everyone's mics that aren't muted.
Yeah, I think it was a dog barking. I mistook that for a question. Maybe the dog had a question. So the first step is where the solar magnetic field shown by this vertical line with arrows pointed down connects with Earth's magnetic field whose arrows are pointed up. So they're able to reconnect. Now the solar wind will blow that open, what is now an open magnetic field line. It'll blow it over Earth as shown here. So that's step 2. Step 3 is it's blown over Earth, and step 4 is that it comes down and reconnects at step 4 shown here. And when it reconnects, it blows plasma away from Earth, shown by step 5, and it also blows plasma and electrons and so on toward Earth, as shown by step 6. And when that happens, you'll generally have aurora and things like that. So the time between step 1 and step 4 is on the neighborhood of maybe 1 to 3 hours. And I see that in my magnetograms all the time, that basically that characteristic time of 1 to 3 hours. So you'll have magnetic reconnection out in front, followed by almost always magnetic reconnection in the magnetotail as shown there. Now the solar wind from Earth looks like it comes out as in a rotating pattern, and kind of like a lawn sprinkler. And by the time the solar wind reaches Earth, it's about a 45-degree angle here with respect to Earth. So that's kind of an interesting fact about the solar wind, the spiral nature of the solar wind. Now let's look at some measurements. This is data that I've taken since December of 2008, which was the start of the solar cycle number 24, and it it ended in December of 2019. So that's right around this time period when it ended. And then solar cycle 25 started in December of 2019 and has ramped up. And according to this plot, which I just downloaded from NOAA just a couple days ago, it looks like we're on the downward side of solar cycle number 25 now. So, but we did have looks like a stronger peak than we did in the previous solar cycle. But anyway, my data covers this whole time period all the way up until I think the latest I have, the latest plot I'm going to show you is like from maybe April of this year. So the first one we're going to look at here is in November of 2018. And this is what you would call a magnetically quiet day. And I see this very, very rarely. In fact, I think I've only seen K0 on all three traces twice in the last 15 years, 16 or 17 years or so. So it's a very rare event to have a very quiet magnetic day, especially at higher latitudes where I'm at. But it did happen, and I think has happened once before that I've seen. Now here's a noisy day, magnetically speaking. This was in December of 2010, and you can see that the magnetic field is just kind of cruising along here. And then all of a sudden we get about 1500, you'll notice there's what looked like noisy episodes, and especially around 1800 through 2100 or so. And I would see these almost from the very beginning when I was operating, when I first set up the SAM-3. And I didn't know what they were, so I just called them noisy days. And it took me a full 10 years to figure it out. But those are ultra low frequency waves. And these are electromagnetic waves that have periods up to 10 minutes. So, but they show up as rapidly squiggling lines. And for a long time, they were actually discovered maybe a couple hundred years ago, but and they were called micropulsations at the time because the amplitudes are really small. You can see that they only have about 20 nanotesla peak to peak on these particular ULF waves here. They've also been called magnetic pulsations, but sometime in about probably the 60s, they changed the name of these types of events to ULF, or ultra low frequency waves. So if you do a search on micropulsations, you'll find a lot of papers written about them, but all of a sudden they disappear about 1961 or something like that. And so if you re-establish your internet search for ULF waves, now you'll see the papers pick up again. Here's another episode of ULF waves. This was early in the UTC day, so this would be during my afternoon. 0-100 in Anchorage is either 3 or 4 o'clock in the afternoon, depending on how the time zones work out. But you can see that these are really noisy, but they're not very high amplitude. And if you home in or zoom in on those, you'll see that they're almost pure sine waves. And in fact, you can analyze the data using FFT, fast Fourier transform, to pull out the frequencies of ULF waves. Now here's just a plain old everyday disturbed day, and this is storm conditions. You can see that the magnetic field was really, really quiet up until noon UTC. And then a storm hit, a magnetic storm hit, and you can see that all three axes made significant jumps. And one of the ways that you can tell a storm condition is if you have your K index properly calibrated, and the construction or the software setup guide gives you guidance on how to do that. You will notice that when you have a K index of 5 or greater, that you can call storm conditions. Now it's not it's not that simple, but for purposes of how I use the SAM3, when I see a K5, I know I've got a disturbance out there that's worth looking into in more detail. The solar flare effect I mentioned. What happens here, and here are the steps that it takes to produce the so-called magnetic crochet. You have a strong, really strong, impulsive solar flare. And you observe this. This is radiation, so you're going to observe it at the speed of light. So it's going to be instantaneous. The radiation suddenly increases the ionization in the upper atmosphere, and so its conductivity is increased really rapidly. And this means that the electric currents that flow in the ionosphere can flow much more easily. And so they do. And the changing current produces a changing magnetic field, which either adds to or subtracts from the magnetic field measured on the ground. And it looks like a magnetic crochet. Now, these are observed most often near the subsolar point. Now, the subsolar point is where the sun is directly overhead. And of course, in Alaska, we never have the sun overhead. In fact, in Anchorage, the highest it ever gets is 53 degrees above the horizon during the summertime. But that doesn't mean you're not going to see them, as I'll show on this plot right here. So this was back in 2014, and you look over here on the at just before 1800, you'll see what looks like a hook, and that's the crochet or the crochet hook. And this one I observed that about 4 hours before solar transit. So in other words, the sun wasn't even near being overhead or directly south of Anchorage. It was more to the east by about 4 hours or so. But that didn't stop it from affecting the magnetic field that I could measure with the SAM3. I think I've only seen maybe 2 or 3 of these, maybe 3 in the last 17 years or so. Here's another storm. And you can see up here on the upper scale that lists the K index, you can see it was K5, which is we call storm conditions, and it was K5 for 3, 6, 9, and about 12 hours. So that was a fairly long storm. And this particular one, according to what I've written on the right-hand side here, is that there was a coronal hole high-speed stream that intercepted Earth, and apparently its magnetic field had a strong southward component, shown here, -7 nanotesla. Doesn't sound like much, but it's enough to reconnect and cause a big disturbance in the magnetosphere. There's some more detail on that particular event. This is the coronal hole shown over here on the left-hand side. It's this dark region. So this is a polar coronal hole. It's up near the pole of the sun. And this is a synoptic map which NOAA produces two times a day. And you can see where they mark the coronal hole here. And then what happens when you have a storm like this is the auroral oval expands, and you can see that this green area here is this so-called auroral oval, the sun's off to the upper right, and normally this oval, it hangs around over northern Alaska here, but you can see where it's been expanded and pushed down and covers Anchorage, which is right in this area right here. So this means that there would have been aurora on this date back in 2017, and and there probably would have been some radio propagation effects associated with that also. Here's another storm, and you can see what happens uh, sometimes. You'll have a real quiet period. For example, this was a 24-hour period where the biggest K index was K3, and that's really a nothing value in terms of magnetic activity. But then about 0200 the following day, then all hell broke loose. And you can see there's some ULF waves in here starting out. And you can see that the red and blue traces have taken a dip, and that's called a magnetic bay. And that really has a strong effect at higher latitudes on radio propagation. So there was very possibly a radio blackout during this period right here in the HF band. Notice that the scales, the vertical scales are the same. The SAM3 software auto scales, although you can turn it off. I usually set it to auto scale, and it scaled up to 2000 nanotesla peak to peak. And you can see that this dip over here at about, what is that? 0745 or so on the next day, reached almost 1750 nanotesla. So that's a really, really strong bay. Here's in May of 2024, there was the so-called superstorm. And I think this was occurred on Mother's Day, so it's also called the Mother's Day storm. But I want to show you an animation here that I got from SuperMag. And what I did is I built this animation starting at about 0730. So that would have been right about here where my mouse is. So this is the start, and you'll see that there was a significant amount of magnetic activity at 0900, about an hour and a half later, and there were several episodes of that. So let's go ahead and play the animation. Okay, that's the first event. And these green lines are the are the vector, the horizontal component of the magnetic field. So these are, they're showing both the amplitude and direction. So we're at about 1400 now. And you'll see something at 1600. And then it quiets down after that. So just for the fun of it, I'm going to slow this down a little bit. So this is the start. And then once we get to about 0900 or so, you'll notice that that's when things really start moving right now. So that's 0859. And then we cruise along for about a half an hour. And there should be another little pulse right there, just before 10 o'clock. And then it's fairly quiet until about, 1330 or so. Right about in there. That's about it. So the SuperMag site, you can basically go to any time and date that you want and get a map like this. And so it's really, and this is something fairly new. this is something that's come out within, I think maybe the last year and a half or 2 years. So this ability is pretty new. I'm suffering a summer cold here, so if I sound like I'm losing my voice, then I probably am. Here's another storm, and this one here is showing Anchorage magnetometer on the left and the HARP magnetometer on the right. Now, HARP is about 400 kilometers to the northeast or northwest of Anchorage. And so what happens at HARP generally has a little higher magnitude because they're at a higher latitude than Anchorage. But you can see that they're pretty close in this in these comparisons. We have a maximum peak of about 1,000 nanotesla at Anchorage and maybe 1,100 or so at HARP. So this particular storm was pretty constant across at least this part of Alaska. But it's interesting to make the two comparisons sometimes. Now, here's an interesting set of plots here. And this one here kind of displays the effects on radio propagation at higher latitudes as a result of a magnetic storm. Now, the upper plot is the SAM plot, with the K index up at the top here. So you can see storm conditions in the third synoptic period here between 0600 and 0900. And it continued for almost the whole day. But down at the bottom is a rheometer data. Now, a rheometer measures the absorption in the D region above HARP. And it's used for HARP experiments. And you can see that every magnetic, whether it's a positive or negative deflection of the magnetic field, it has an effect on the D region ionosphere. So you can see that this little blip right here on the rheometer lines up perfectly with this positive, almost 200 nanotesla deflection here. And you can see several of these, and they seem to be getting stronger and stronger as the day goes by. And the magnetic field, the magnetic bays get stronger and stronger as the day goes by. So this last event here at about 1500 was fairly strong and caused about 2 dB of absorption in the rheometer data. Now, this rheometer data is taken at 30 megahertz. So when you translate that frequency down to the lower HF band, say 5 megahertz or so, then that 2 dB of absorption at 30 megahertz translates to like maybe 70 or 80 dB at 5 megahertz. So this is kind of interesting to see how the magnetic field and D region absorption at higher latitudes work together. And they work against you because whenever you have D region absorption, then there's going to be no radio propagation through it. Oh, and I forgot to mention that there was also ULF waves here in the 16 or 15 to 1800 time period. That corresponds to the morning time. So this would have been in the morning sector when these ULF waves occurred. Now, sudden impulses. These are really interesting, and I've spent a lot of time studying on these. In fact, one of the links that you have in the chat will take you to a list of papers that I've written on the magnetic field, measurements that I've taken, and one of those papers talks about sudden impulses in great detail. So what's shown here is there's going to be some kind of a flare, and when a lot of flares have a coronal mass ejection associated with them, a CME. And this image over here on the right shows the actual flare that I'm going to talk about here in a second. This was in December of 2020. So there was a flare and a CME. And coincidentally with this, the CME produced slow sweep radio emissions from the sun. And this is called a type 2 radio burst. So this particular event here not only caused magnetic field disturbances, but also some interesting radio phenomena. So this is the sudden impulse over here on the left side, just after 0200. And this particular sudden impulse had an amplitude of 65 nanotesla. That is up there, probably one of the strongest that I've ever seen. And I've seen quite a few, probably a few hundred sudden impulses that I've seen. And this is one of the stronger ones. Now, when you look at this, you say, well, that's a step function and or an impulse function. But it looks like that on a 24-hour plot. But if you zoom in on that, you'll see that it's got some slope to it, and both rising and falling. And I'll show you some of those here in just a second. I've got to wet my whistle. Here's another sudden impulse. This was in 2021. And the SAM3 graph is auto-scaled here, so it shows the effect of the sudden impulse. Now, this is where the sudden impulse occurred right here, and I've zoomed in on it. You can see that it's got actually 3 peaks to it. And a storm followed. A storm, it took, 5 hours for that storm to start after the sudden impulse. Whereas the one we just looked at the day before, the slide before in 2020, this one was a really strong sudden impulse, but nothing happened after it, at least for the next 20 or so hours shown on this plot. But this one here, 5 hours later, there was a storm that followed this sudden impulse. Now, what I did here is I've zoomed in on the sudden impulse for May of 2021. And you can see that just before the actual rise of the impulse, there's a small dip. And you see that, or at least I see that all the time. There will be a small dip that precedes the actual impulse itself. And so you have this fairly sharp rise. And this looks like we've got about 1 minute and 40 seconds per division here. So this one took a couple minutes to rise, and there was some activity that followed it. This is for Anchorage on the red, and the blue then is at the HARP, the Gakona site that I have. You can see the shape is roughly the same. There's a little tiny dip followed by a rise. You can see some features here, like this double peak at the top corresponds with this double peak at Anchorage. There's stronger sub-pulse here at 0650, and you can see that at HARP as well. Doesn't appear to be quite as strong, but it's really interesting to zoom in on these sudden impulses and see what their shape looks like under a microscope. Now here's that same one. Anchorage is the red. The green now is taken at the Isle of Mull in Scotland. So this fellow in Scotland, Roger Blackwell, has got a SAM3 that he runs, and he's basically on the other side of the world from Anchorage. But you can see that the sudden impulse was recognizable on his SAM3, but he doesn't have the dip like I do, like I see. He's at a lower latitude, and I have a feeling that has something to do with it. But you can see that he has a fairly strong peak. He doesn't have this secondary pulse like I saw. He didn't have that at all. One of the things that I've been trying to do over the years is determine if I see a sudden impulse at, let's say, 0600 right on the nose, does everybody on the Earth see that sudden impulse at 0600? And so far, we've drawn no conclusions on that after 15 years. In fact, there's been papers written on that subject, and those papers don't draw any conclusion either. So it's kind of a tough nut to crack, but it's still really interesting to look at sudden impulses. Now, coronal hole high-speed streams. What you have there is the sun's magnetic field more or less is dipolar. It's not really, but it's close enough for talking purposes. You'll have closed magnetic field lines on the sun, shown in red, and then you also have these open magnetic field lines that stretch out into space. Now, we've always learned that there's no such thing as an open magnetic field line, and this is still true, although we call them open here, shown in blue. They stretch out into space a long ways, maybe to the edge of the solar system, but they always loop back and come back and connect at the sun itself. Now, if you have a coronal hole, what happens is that you have these open magnetic field lines, and that allows the release of this high-speed stream. So whenever you have a coronal hole shown as a dark region in some of the imaging that you look at, there's going to be a higher speed stream. And the speeds are in the neighborhood of maybe 500 to 800 kilometers per second. So they're substantially faster than the what you would call the background solar wind, which is in the neighborhood of maybe 300 to 400 kilometers per second. Here's a persistent coronal hole shown here. So this is on day one, and this is the solar 27 days later. So this would be one solar rotation, and then another 27 days later, you can see the coronal hole still exists. So that's called a persistent coronal hole. So every 27 days, if this magnetic field associated with this coronal hole can interact with the magnetosphere, you'll see some kind of a disturbance 27 days later. Now here's a plot taken where I've spliced 3 days together, and so this was a coronal hole that moved across the sun. I got 3 days of it. It became geo-effective or Earth effective for about 3 days. You can see that there's it raised up and then quieted down, and then raised up again the next day and quieted down, and then started getting really, really disturbed later on the third day of this plot. So now, if I hadn't known that there was a coronal hole high-speed stream impinging on Earth, this plot would have been meaningless to me. But Space Weather Prediction Center has a spacecraft up there called ACE that detects these, and they report them, and so I know about so I can know about them. Co-rotating interaction regions. This is where you have a fast solar wind, maybe associated with a coronal hole, that catches up with the ambient or slow solar wind, and that has a shock front associated with it. And that shock front, of course, has an embedded magnetic field, and if it's in the wrong direction, in other words, southward, it's going to reconnect with Earth and cause a problem. So here's a plot from the 1st of January in 2011, and you can see that the magnetic field was really, really quiet until the arrival of a co-rotating interaction region. So this precedes a coronal hole. And then you can see the arrival of the coronal hole about 4.5 hours later over here on the right. And you can see that the magnetic field started a very deep bay at that time. So again, I wouldn't have known this was a coronal hole that caused this without the Space Weather Prediction Center. The co-rotating interaction region is something that you can't identify on the ground. So this plot here, you can see there was a mild disturbance about 0900, and then a few hours later, several hours later, the arrival of this co-rotating interaction region, and it didn't really look that much different than the earlier part. So there's no way I would have known about that if I hadn't seen the report. Now, the solar sector boundary crossing is kind of an interesting thing. As the sun rotates, you have the north magnetic field lines that go away from the sun, and then you have the south magnetic field lines are going toward the sun. In between those is what's called the heliospheric current sheet. And now the space between Earth and the sun is filled with plasma, and the plasma is almost a perfect conductor. There's no, it's so thin that there's no chance for collisions and losses. So it's a really good conductor. But as the sun rotates, it forms these folds that you can see on this right image. And this is kind of like a ballerina skirt. As she twirls, the skirt will have these folds in it. So this is what you see here with this heliospheric current sheet. The sun's in the middle. Earth is this tiny little dot right here. And so each time one of these folds passes Earth, then you'll see you might see some kind of activity. So here's one shown here. You can see that up until about 0800 or so, there was really not much happening. But then after the solar sector boundary crossing intercepted Earth, or Earth intercepted it in its orbit, then you can see that there was mild disturbances. Weren't very much though. K3, K2, those really aren't a whole lot to be running home to mommy about. Here's another solar sector boundary crossing. This one here almost caused a storm, not quite. K4, not storm level, but approaching it for sure. Now, one of the other kind of nice things about the SAM software is that you have you can produce some statistics from it called a Bartles diagram. And this is named after Julius Bartles. He was a really super smart magnetic field guy. And this is going way back into the 20s and 30s and 40s. And he realized that the sun takes approximately 27 days to rotate. So he built this calendar based on a 27-day rotation period. And a lot of times you can, when you plot these out for each rotation period and then overlay them like I'm showing here, you can see that disturbances, this is in a K index shown here on the vertical scale. So if you have a high K index, or storm conditions, they will show up on each rotation. So here we have a disturbance that came back around on the sun 27 days later, but was gone by the next rotation in December. So this is something that you can do. It's not an automatic feature that is produced automatically. You have to actually load the data and tell it what dates to use, and it'll produce the Bartles diagrams for you. So that brings me to the end. And again, these web links that I'm showing here are in the chat. I've got the links for the real-time data at Anchorage and HARP. Maybe kind of handy for you once you get your SAM3 in service. You can, if you see something going on, you can compare it to the ones I have up here in Alaska. You'll need to remember, though, that at higher latitudes, the magnetic field is much more active than where you are. I think you're at like maybe 43 degrees north latitude down there. And so you're going to have a much more quiet magnetic field. But when you do see an event, you probably know that something has happened, and you can compare it to Anchorage. Now, this third link here, which is in the chat, this takes you to a web page where I've posted articles that I've written on magnetism and the SAM3. And that's where the sudden impulse study is, and a whole bunch of others. There's quite a few papers there that you can read if you don't have anything else to do. Space Weather Prediction Center, absolutely essential for magnetic field studies on the Earth. They have a whole range of reports that you can get via email, and they send them out automatically. All you have to do is subscribe, and they're really, really helpful in identifying magnetic anomalies that you see on your SAM3 once you get it going. The SuperMag site, remember I showed you that really cool animation? You can do those, set that up by going to the SuperMag. International Real-Time Magnetic Observatory Network. You can find, you can get to observatories, magnetic observatories around the world. The solar cycle progression that NOAA produces, they update that thing, I think, every day. And so that's kind of interesting to see how the cycle is going. The USGS maintains a bunch of stuff that is really, they have some really good tutorials there, and you can also get access to the real-time plots for all the observatories that they operate in the United States, including they have several up here in Alaska. Solar Dynamics Observatory, or SDO, is a spacecraft that was launched, a number of years ago. I don't remember now. I think it was maybe 2013 or something. And it produces images of the sun. So you can get, if you see a flare-induced effect or a coronal hole mass ejection effect on your magnetometer, you can go to SDO's website and get a picture of the sun as it was doing what it is you're seeing. And then, of course, there's the tutorial that I wrote a few years ago that you can download and read when you don't have anything else to do. So that's pretty much it. And let me see if I can unshare here.
Well, that's awesome.
There we go.
I've never known so much about magnetism. I mean, that is just amazing. Amazing that you can actually do what you do.
Well, I'll tell you, Paul, when I first turned that machine on, and I'd see every time I'd see a squiggle, I'd say, what is that?
Oh, geez.
And it took me a long time to figure it out. And get Space Weather Prediction Center, find out about them, and learn about it. And so that's the key. You have to do a little bit of studying, and but it's well worth it.
Well, you could. I mean, every time I look at that, I can say, man, that's all that stuff is actually what made us originally. I mean, the activity of the sun, and so much going on there with the different particles and stuff like that. I said, man, all those things came together and made, made people.
Right.
And it is what we are now. So
Yep.
just amazing looking back in history, just looking at that. But I'm just fascinated by what you've done. I wish I could understand all of it, but it'll probably take me a long time.
I wish I could too. There's so much to it that you almost have to kind of pick a subject and then concentrate on that because the field is so wide in terms of things that you can learn about it that it's almost impossible for one person to really get good at everything.
Well, you got a real treasure trove of information there with all those links, and if somebody wants to make a career, this is the place to start.
Yep.
Any other comments from the crowd? Any other questions that might be going on? Anybody have any questions for Whit?
Just a quick comment here, Paul. This is Roger. I am now working on the platform for the new receiver or new feed, and if someone else wants to finish the work on this magnetometer, they're more than welcome to. It's not like I'm trying to bogart it. If someone's really inspired to work on it, I'm more than willing to give it to someone else. Otherwise, excuse me. Otherwise, I will get to it, but it's just getting pushed down by other projects.
Well, I'm sure we got some smart guys that are in our club, and I think if we make a point of it, maybe we can get some discussions going around it and get you and get some more folks that are interested in making this happen. But I'm very excited about it.
Yeah, and I'm really looking forward to you guys getting yours online down there because I don't have any lower latitude type magnetometers in the US. So I'm really interested to see how you guys, what you see and able to compare it to what I see.
Well, we'd love to do that. Well, thank you so very much for the 3 sessions you've given us, and that's a lot of really great information for everybody here. Thanks
Yeah,
again.
I'm glad to do it.
Thanks again for doing all this for us.
Yeah, you're welcome.
All righty. Well, I will say goodbye, and thanks everybody for joining us tonight. And if I can get it done, I'll see if I can get the recording and put it up on our DSES YouTube page. Thanks again, Whit, for everything, and I hope you don't be a stranger. Come on back and join us sometime. If you're down,
I'm hoping to.
If you're down in the lower 48, you got to come by and see our dish.
I'm hoping to.
Okay.
Okay, see you guys.
Yeah, thanks, Whit.
Thank you.
Thank you very much.
Paul,
Thank
before
you.
before you go, yeah, I'm at the site. I got in late, but you did record this, right? So I can get back to it.
Yeah.
Okay. Our fiber connection is working well.
You look good. You're not even stuttering.
I don't look like Max Headroom, right?
No.
You're there at the site, Bill?
Yes.
Oh, awesome.
Yeah, I'm in the control room. And I don't know, I don't know how to get rid of the, I'm really unsure of how to get rid of the background, so I can show you the.
It looks fine.
But bottom left corner, there's the video image. There's a little caret that will open up a drop-down menu, and then you can choose or adjust the background and effects.
Oh, that's right. So I can say none, probably, right?
Mm-hmm.
I don't see it. I don't see the none. But anyway, so yeah, we're we got the 408 feed put back up today and tested the receiver. And we're all ready to go for the crab pulsar early tomorrow.
Bill, could you take a couple pictures of that